All right, so we're going to talk about integration, and in layman's terms, integration is basically the area under a curve. In this course, we're going to deal with shapes that are not what are considered to be classical geometric shapes. So when I say classical geometric shapes, or you may hear me say classical geometry, classical geometric shapes or classical geometry are basically the formulas that we were exposed to prior to this course. For example, if we're dealing with a circle, we can find the area and the perimeter of a circle, right, by use of some formulas, right? There's a formula to find the area of a circle. There's a formula to find the circumference of a circle. We can also find the area and the perimeter of a rectangle, triangles, spheres, cones, that sort of things. These are all classic geometric shapes, and there are formulas to find such areas. However, if we take a look at a curve such as this one, right, this is actually on an x and a y axis, and this is the graph of 1 minus x squared, and its graph on the x interval from 0 to 1. And let's say we were asked to find the area for this figure. The area for this figure can't be found by a simple geometric formula because it's not a simple geometric shape. However, we can estimate the area of such a shape by using rectangles. Okay, so I want to review a rectangle. Okay, and at this point I would switch to the document camera, which is not working at this time. So I'm going to switch to OneNote. So just give me a second and let me bring that up. And I'm actually going to let me turn this on first of all. All right, so now I think I'm where I need to be. So we're actually going to review a rectangle. Okay, and in a rectangle is basically just a quadrilateral figure, which means it has 4 sides, and the opposite sides are parallel and congruent. So we have the length and the width. So some people may call this the height and the depth, but I'm going to use the length and the width. We can find the perimeter, which would be the area around our figure. So it's twice the width plus twice the length. We can also find the area, which is simply the length times the width. we're going to use a series of rectangles to estimate area. Okay, so this is basically called Riemann sums, or estimating by finite finite sums. And what we're basically going to do is estimate the area by a use of rectangles. Okay, now this is where the book we were using last semester and the terminology in the book we're using with XYZ they're sort of conflicting. There's something from just regular textbooks that are something called an upper estimate. Okay, you can find the upper estimate. You can find something called the lower estimate. And you can also find something called, you can find the area using what's called a midpoint. So I'm just going to explain these. If we look at these two figures, all right, this first figure is this curve we were looking at earlier, and its area is being estimated by two rectangles. These rectangles are considered to be an upper estimate. Notice that for our rectangle, there are a portion of our rectangle that exceeds our curve, which would give us an area slightly larger than our actual area, which terms this as an upper estimate. The more rectangles we use, the better our approximation. So notice this is still an upper estimate using 4 rectangles, right? So we can find the area for every rectangle by simply multiplying the length times the width, adding those up all together, and that would give us the area. There is another method called the lower estimate. So if we take a look at this lower estimate, notice that this uses a total of 4 rectangles, but notice that each rectangle is underneath our curve, which means that if we were to add up all 4 of our areas, it would give us an area that would undershoot or an underestimate of our true area. And then next we have something called the midpoint. So notice that if we are using this midpoint to estimate the area, notice that a portion of our rectangle is underneath the curve and a portion of our rectangle overshoots the curve. Here again, we can find the area by finding the area for all 4 rectangles and adding up these areas. In the XYZ textbook, they don't use upper estimate, lower estimate, or midpoint. They use left endpoint and right endpoint, right? We would find the area by using a right endpoint and 4 rectangles, or a left endpoint and let's say 4 rectangles. So here's what the left endpoint and right endpoint mean. All right, so I'm going to go back to our first figure. If I actually look at my first figure, this first figure would actually represent a left endpoint. The reason why this would represent a left endpoint is because as we look at our rectangle, right, the left-hand side of our rectangle, it serves as the height. Right, so this would be considered a left endpoint. If we're looking at a right endpoint, notice that here we're using 4 rectangles. Notice that the right side of our rectangle serves as the height. Right? So for example, if you wanted to find the area for this rectangle, you would simply multiply the width, which in this case looks like it's 0.25 times the height. The height is 15/16. Another way you can actually get your heights is you can take your endpoint value and you can substitute that into your equation. All right, so we're going to take a look at a couple of examples. We're going to find the area using a left endpoint, and then we'll find the area using a right endpoint. All right, so I'm going to return back to XYZ, and for this first problem, we're asked to use 4 rectangles to approximate the area for the graph, the area under the curve for this graph, which is 0.2x cubed minus 1.6x squared plus 13 over the intervals from 2 to 9, and we're asked to use a leftmost endpoint. All right, so the first thing I'm going to do is, even though the problem doesn't ask for it, I want to get a visual representation of our actual problem. So I'm going to bring up the graphing calculator. Which is here. And I'm going to graph. So I'm going to go to y equals, and I'm going to put in 0.2x cubed minus 1.6x squared plus 13. I'm going to hit zoom and 6. So what zoom 6 does is sort of puts it in a -10 to +10 increments of 1 for both the x and the y axis. All right, so this is our curve, and we want to estimate over the interval from 2 to 9. Okay. I'll tell you what, instead of doing this one, let's look at number 3. Okay, and the reason why I say number 3 is because this is not necessarily a straightforward type problem now that I'm kind of looking at this. So we're actually going to start with number 3. Okay, sorry about that. Then we'll kind of jump back to number 1. I apologize. And I'm going to just generate another problem. Okay. All right, so I want to just kind of start with a straightforward type problem first. I apologize. So here again, we're asked to find the area using a left endpoint. Okay, but in this case, we're using f of x is equal to 1.2 times the square root of x. Now, unlike the first problem, here we already have a graph, right? If I were to just regraph that in my calculator, I have 1.2 times the square root of x, and I'm going to use zoom 6 to graph. All right, and just notice the two graphs are similar. Right? So here we're asked to approximate the area from the x interval from 3 to 6 using a left endpoint and using three subdivisions, which would equate to 3 rectangles. All right, so I'm going to go back to OneNote. So I'm just kind of make a rough sketch of what's going on. So this was 1, 2, 3, 4, 5, 6. So we want x equal from 3 to 6. And we want 3 subdivisions. So the first thing I want to do is I want to find the rectangle's width. So here's the formula. The rectangle's width is equal to the upper limit minus the lower limit divided by the number of rectangles. Right. So what is the upper limit and what is the lower limit? Well, the upper limit, and I'm going to switch screens here for a second. The upper limit is 6 and the lower limit is going to be 3. Okay, so the upper and the lower limit are basically the interval on x in which you're working. So this is 6 minus 3. The number of rectangles we're working with is also 3 because we're looking for 3 subdivisions. So the width of each rectangle should be 1 unit. So our first rectangle runs on this interval from 3 to 4. The second rectangle runs on this interval from 4 to 5, and the third rectangle runs on this interval from 5 to 6. For each rectangle, we're asked to use a left endpoint. So for my first rectangle, it's on this interval from 3 to 4. Since I am using a left endpoint, I'm going to use the height at 3, right? Because on my first interval from 3 to 4, the left endpoint is 3, so I'm using 3 as my height. So this kind of serves as an underestimate, right? So this is rectangle 1. My second rectangle lies on the interval from 4 to 5. I'm going to use the left endpoint, which is at 4. So 4 serves as the height. And that's rectangle 2. And our third rectangle runs on the interval from 5 to 6. So we're going to use 5 as the height because that's the leftmost endpoint. And we have rectangle 3. And that should be a 3. So now we want to add up, well, we want to find the area for all 3 rectangles, and then we're going to add up the areas, and that would give us the area under the curve from 3 to 5. Excuse me, from 3 to 6. So we're going to find the area of rectangle 1. Right, so that A sub R1 is simply the area of rectangle 1. So in order to find the area of rectangle 1, we're going to take the width, right, which is 1, times the height, which is f of 3. All right, so I have my length here, right, which is 1, right, and we found 1 here earlier, times the height. Since we're taking this left endpoint, we can find the height by taking 3 and substituting that into our function, right, which we'll do in a second. Now we can find the area of rectangle 2. Right, we can simply find the area of rectangle 2 by multiplying the width, which is 1, times the height, which is f of 4, we can find the area of rectangle 3, right, by taking the width, which is 1, times the height, which is f of 5. So now we'll find all 3 heights. Excuse me, we'll find all 3 areas, and then we'll find the total area by adding them all together. All right. Now, in order to make these calculations a little bit lighter, I'm going to use the graphing calculator. All right, so I'm going to turn it on. I'm going to go back into y equals, and notice we have the 1.2 times the square root of x. If I want to find f of 3, there's a couple of ways I can do this. I can simply put in my calculator 1.2 times the square root of 3, right, and that would give me the value. Or, okay, I'm going to go back to my home screen. I can hit vars, which is short for variables. I can scroll over to y variable. I can hit function. Okay, I hit the wrong button. So variables, y variable, I want function. I want y sub 1, right? Because we have y sub 1 stored as 1.2 times the square root of x. And I can evaluate that when x is 3. And I get 2.078, right? I can also find the function evaluated at 4. And I can also find the function evaluated at 5. Okay. All All right, so I'm going to just jot these things down, and I'm actually going around. So I have the area of rectangle 1, that's 1. So keep in mind that 1 is the width times the height, which is f of 3, which is 2.078. We have the area of rectangle 2, which is 1 times f of 4, and f of 4 is 2.4. And then we have the area of rectangle 3, which is 1 times f of 5, which is 2.683. Now, in order to find the total area under the curve, it's basically the area of rectangle 1 plus the area of rectangle 2 plus the area of rectangle 3. Right? And if we were to add those all up together, we would have, and I'm just going to let the calculator do it. And this is where the calculator can make the calculations a little bit easier. And we have 7.16. Now, since this is a couple things. Since this is area, it's in square units. Okay, so I don't think you have to put units in, but I just want you to keep in mind, so this would be unit squared. Okay, so whatever our units are. Now, just one thing, the more rectangles you use, the better your estimate. All right, so notice here we used 3 subdivisions, which are 3 rectangles. We use a left endpoint. Okay. All right, any questions about this first example? Okay, now we'll find a question that uses a right endpoint. Okay, this one was also a left. Okay, we'll take a look at number 2. All right. Okay, so here again, there is no curve, right? We're simply given a function. We're simply given the interval on the function, and we're given the subdivisions. All right, so here we're asked to approximate the area under the curve y is equal to x squared. So I'm on a graph. And from college algebra, whenever you graph equations with the highest power as a square, then you are dealing with a quadratic equation. Okay, so this is y is equal to x squared. From x equal to 2 to 4, all right, so from 2 to 4, we want to find the area using a right endpoint and 4 subdivisions. Okay, so that sort of looks something like this. This is 1, 2. Let me start that over. So this is 1, 2, 3, and 4. So this is our graph. Y is equal to x squared. And our interval is from 2 to 4. And we want to use 4 rectangles. So first we need to find the width of each rectangle. So the width is going to equal to the upper limit minus the lower limit divided by the number of rectangles. So our upper limit is 4. Our lower limit is 2. The number of rectangles we want is 4. So we have 2 over 4 or 1/2. Okay, let's make my pen start right. 1/2. All right, so each rectangle should be 1/2 unit wide. Okay. So we're on the interval from 2 to 4. So our first rectangle is going to run from 2 to 2.5. So that's 2.5. All right, and we want a right endpoint. So my interval from 2 to 2.5, 2.5 is my right endpoint, so that serves as the height. And I just erased my line. All right, so this is rectangle 1. All right, so I'm going to do this all in one step. So we're going to write out the total area. All right. So for rectangle 1, in order to find the area of rectangle 1, excuse me, we must take the width, which we calculated as 1/2, times the height, which is f of 2.5. So this gives me the area for rectangle 1. That's my width times my height, or my length times my height for the first rectangle, plus the second rectangle runs on the interval from 2.5 to 3. We're taking the right most endpoint, so we're going to take the endpoint at 3. And my lines just keep disappearing. So this is rectangle 2. So for the area of rectangle 2, we have the length, which is 1/2, times the height, which is f of 3. Our third rectangle, so that's the area of rectangle 2. Our third rectangle runs on the interval from 3 to 3.5. So 3.5 serves as the height. So we have 1/2 times f of 3.5. And that's the area of rectangle 3. Our fourth subdivision, or our fourth rectangle, is on the interval from 3.5 to 4. So our height is at the rightmost. So the area of rectangle 4, that's 1/2 times f of 4. Right. So before we go any further, are there any questions on this formula, this function? All right, we simply wrote out the area for all 4 rectangles, right? The width of each rectangle is 1/2. The height for each rectangle is the right endpoint. All right. So now I'm just going to put this in the calculator. So based on what we did in the last example, I'm going to go back to y equals. All right, and we have x squared for y equals. I just want to check my function. And this is basically what I'm going to put in. So I'm going to put in 1/2, or 0.5, times our function evaluated at 2.5. So I'm going to recall our function by using variables. I'm going to scroll over to y variables. And under y variables, we want the function. Right, and the function we want is y sub 1. We've stored that as x squared. And we want to evaluate at 2.5. Just remember, when you're using this variable key and when you're evaluating functions, you must use a set of parentheses. All right, so notice I'm using y sub 1 and I'm evaluating that at 2.5, but I'm putting or encapsulating 2.5 in a set of parentheses. Plus 1/2, or 0.5, times our function evaluated at 3. Plus 1/2 times the function evaluated at 3.5. Plus 1/2 times the function evaluated at 4. And we have an area of 21.75. Okay, I'm in one though, so if I put something in, it may conk me out of it. Oops. All right, so I'll go back. So this is 21.75 square units. All right, any questions about using, now this is called Riemann sums, even though they aren't actually terming it as Riemann sums in this particular textbook, but this is just Riemann sums, and Riemann sums in layman's terms is basically finding area by the use of adding areas of rectangles. So now in this first section, dealing with integration, we won't actually use rectangles in this course. We're going to use some formulas basically to find area of these non-classical geometric type shapes. I've posted an integration video in the Blackboard announcements page. I'm going to go back to that announcements page. Okay, I actually posted a couple of videos on the announcements page, and I sort of jumped the gun. I did not actually watch these videos before I posted them. This video, rules for integration, and this integration video, when I recorded this last semester, the Riemann sums topic was first, but I forgot to record it. All right, so as I was kind of going back, I posted these two things, not really knowing I didn't talk about Riemann sums. So after today's video, Riemann sums, these things should make a little bit more sense to you as far as what's going on. But just in a nutshell, integration is finding the area under a curve. All right, so I'm going to go back to, okay, so it didn't cut out. All right, I flipped my laptop around. I'm going to go back to the shared camera. All right, so now I'm back on my camera. I have two cameras in the office. I have this camera, which I intended on writing from, but for whatever reason, I believe something's wrong with my dock here, where everything's hooked up to. I have to get ISN in to work that out. So for class on Thursday, I will probably have a pre-recorded lecture. Okay, just so I won't kind of deal with some of the things that we're dealing with as far as my computer going out. This is actually my second time using OneNote, so I'm surprised that went as well as it did. I posted the integration videos on the announcements page. For Thursday's class, we will not meet this Thursday's class. I actually posted those two videos before we went over what we did today. I'm going to try to pre-record a lot of the videos for this course, mainly for future classes. Okay, I'm going to go back for 1 second. Okay. On this announcements page, there are actually a difference in these videos, and I want to explain the difference. This first video is kind of like a grainy, choppy type video. This video was actually recorded last semester. If you looked at it, it's sort of glitchy. The video, it kind of goes in and out. This second video, right, it was recorded not necessarily in a studio, but it was recorded in a better fashion. The audio is a lot better. I've created these PowerPoints. It took me quite a while to create these PowerPoints to make them kind of do what they do. The videos that I'm going to basically take the pre-recorded lectures from last semester, and I'm going to put them in this format where I'm going to try to make PowerPoints of the videos. I want the audio to be nice versus this sort of thing. Okay. So I'm in the process of taking all of the lecture videos, reworking those into a better format, and just to kind of build up this XYZ course. As you go through the course, this course was actually created by, I believe, someone at another college, community college in North Carolina. There were no videos whatsoever. So as I make videos, I'm gonna make them a part of this open source kind of deal. So there will be some video, not more so the like view an example like there was in my math lab, but I'm going to try to fill this course with as many video lectures as possible. So I just wanted to just kind of forewarn you, on Thursday we won't actually meet live, but I will post a pre-recorded lecture. Next Tuesday we're going to meet live again. Okay. All right. All right. So are there any questions about anything thus far? I did have a question, well, a concern from one student. They said that they had completed some homework, and when they logged back in, it sort of disappeared on them. If that has happened to you, just send me an email, and we're going to try to figure out what's going on. That may have been something that I have done. I'm not sure. Just like I said, we're still trying to work out some of the bugs. And one of the things I found out is if I'll make an assignment, and if you all go in and actually start on the assignments, and then if I in turn go back and change something, it may mess some things up. So I don't know if that's what happened in that particular case or not, but we're going to get to just kind of get to the bottom of some of the glitches and quirks that are kind of going on. So if there's anything that you kind of run into such as that sort of problem, just email your concern to me, and we'll kind of just look into that. All right, so are there any questions about anything up to this point? And I should go back. Okay, so I'm going to stop the recording.